What is actually the farthest point in the universe? Is it the Big Bang, the edge of the universe? Or is it the light that emanated from the first star? The James Webb Telescope may now have reached the furthest point of the observable universe. This discovery was completely unexpected, and once again, we marvel at the incredible discoveries and new dimensions that this telescope is showing us. Scientists now have to face the truth, and they are stumped. The recent discoveries with the JWST have once again shaken up the astronomical community. These new findings have the potential to completely revolutionize our understanding of the universe. Once again, the JWST may have reached the most distant point in the observable universe and shown us structures that are almost impossible to see. Using the gravitational lensing effect, the JWST has observed 5 extremely dense protoglobular clusters. These clusters are located in the cosmic GEMS arc galaxy, which existed only 460 million years after the Big Bang. This discovery provides us with an unparalleled view of the earliest phase of star formation in the universe. Even more surprising is the discovery of a galaxy that existed only 290 million years after the Big Bang. This galaxy, named JWST 14, is the farthest point in the observable universe and is the oldest galaxy ever observed. This galaxy is exceptionally bright, suggesting that it's several hundred million times the mass of the Sun. The question arises as to how the universe was able to form such large and bright galaxies in such a short time after the Big Bang. Einstein's theory of general relativity explains that gravity is the result of the curvature of spacetime by matter and energy. This curved spacetime determines the paths that energy and matter follow. Light, which normally travels in a straight line, can be deflected and amplified by the gravitational force of massive objects. This phenomenon, known as the gravitational lensing effect, allows astronomers to observe distant objects that would otherwise be too faint or too far away. The JWST has used this phenomenon to observe the cosmic GEMS arc galaxy, which got its unusual name from its optical resemblance to a very fine crescent moon. Without the gravitational lensing effect, its light would have been too faint to be detected with current technologies. The old Hubble Space Telescope had already provided clues about the galaxy. However, Hubble's images were too blurred. The JWST has now used its near-infrared camera, NIRCam, to investigate this discovery in more detail. The spectrometer, which can measure infrared radiation in particular, showed that the diffused light really is a separate galaxy that appears very small and low in luminosity. Further analyses will now show how this galaxy was structured and what kind of stars and elements it contained. The upstream galaxy cluster SPJ 615574, which is itself around 4 billion years old and contains thousands of galaxies, acted as a gravitational lens. Gravitational lenses are a stroke of luck for science. Thanks to them, we can also study smaller objects such as the cosmic GEMS arc galaxy. The study of this galaxy now allows astronomers to look back about 97% of total cosmic time, which puts us at about the time limit of the observable universe. But you have to keep in mind that we are talking about the observable universe. That doesn't mean that there isn't more. This is the exciting question at the moment. How big and how old is the universe really? We thought it was 13.8 billion years old, but now we see galaxies that already existed 300 million years after the Big Bang. This cannot be true, and we have to assume that the universe is much older or even infinite. This would mean that we still have a lot to discover. What did the protog-globular clusters in JWST 14 reveal? Only around 290 million years after the previously assumed Big Bang, so-called protog-globular clusters formed in the galaxy JWST 14. These clusters are considered to be the precursors of today's globular clusters, which consist of hundreds of thousands of stars. By observing protog-globular clusters in this early galaxy, scientists hope to gain valuable insights into the conditions and processes of star formation at this epoch. At the moment, every clue counts if we want to find out what really happened at this time and whether these galaxies are really young galaxies. The clusters are highly interesting because they formed from dense gas clouds and began to form stars very quickly. The JWST again used its NIRCam to observe and analyze these early structures with high precision. In the spectroscopic investigations, the properties of these protog-globular clusters could be determined, and thus we have interesting new insights into the composition and evolution of early star clusters. The study of protoglobular clusters in distant galaxies could not only help us to find out how the first structures in the universe were formed, but can also provide us with valuable clues as to how matter in general was formed. Once we have deciphered this, we will be a lot closer to the origins and blueprint of the universe. Researchers also hope to use the distribution and dynamics of the protoglobular clusters to find clues about the distribution of dark matter in these early galaxies. Dark matter is thought to have significantly influenced the evolution of galaxies and makes up a large proportion of the matter in the universe. However, we do not yet know exactly whether it really exists and what its exact physical properties are. Last but not least, the protoglobular clusters within the cosmic GEMS arc galaxy should provide new insights into the epoch of reionization. During this period, the universe is believed to have been permeated by neutral hydrogen, which eventually ionized and ushered in the cosmic dawn. Did the cosmic dawn not exist? Imagine an infinite universe. There could not possibly have been a dawn. But until now, this idea has been an integral part of our cosmology. Let's go on a journey together to this theoretical cosmic dawn. Scientists see this point in time as a crucial phase in the history of the universe, around 300 million to 1 billion years after the Big Bang. The transition of the universe from an opaque state to a transparent one took place. The dark universe was still dominated by neutral hydrogen. It was like a foggy soup. Then, with the formation of the first stars, reionization set in and it became light. The universe was clarified by the chemical processes, and light was able to spread freely. Researchers call this time the cosmic dawn. The time before this was opaque, and as we could only observe visible light with our telescopes, there was little hope that we would ever be able to see beyond the cosmic dawn into the cosmic night. Researchers imagine the scenario before reionization as follows. The Big Bang was the starting gun around 13.8 billion years ago. From second 0 to 20 minutes after the Big Bang nucleosynthesis took place. In these first minutes after the Big Bang, the universe was extremely hot and dense. During this phase, the first light elements were formed, consisting mainly of hydrogen and helium with some traces of lithium and beryllium. This phase ended when the universe had cooled down to such an extent that nuclear fusion within the extremely hot primal soup ceased. Approximately 370,000 years after the Big Bang, the recombination epoch followed, and the universe cooled further, leading to the formation of neutral hydrogen atoms. This epoch marks the point in time when the universe began to thin out a little as the photons were no longer constantly colliding with free electrons. It was precisely this recombination that produced the radiation that we can still measure today as cosmic background radiation. At this time, the universe was still dark. There were no stars and no light. The Dark Ages lasted from around 370,000 to 300 million years after the Big Bang. During this time, the universe was mainly filled with neutral hydrogen and helium. The temperature of the universe continued to fall, and the first structures formed under the effect of gravity. The cosmic dawn began when the first stars and galaxies formed. The first stars are often referred to as population 3 stars. They were extremely massive and short-lived, producing large amounts of ultraviolet light which was eventually able to ionize the neutral hydrogen. With the ionization of the intergalactic medium, the radiation of the first stars spread out. Initially, ionized bubbles formed around the first light sources, and over time, these bubbles merged, and the universe became more transparent. The chemical processes during reionization were complex. The ionizing radiation, which was mainly in the ultraviolet range, had enough energy to knock electrons out of the hydrogen atoms and ionize them. In addition to hydrogen, helium, which is freely available in the universe, was also ionized. However, these processes took place at completely different energy levels and did not have the same effect as hydrogen ionization. Was it all just a dream? It all sounds good so far, but we have a problem with this theory. Since the discoveries of the James Webb Telescope, we know of galaxies that are so far away that their light comes from a time less than 300 million years after the Big Bang. One of these galaxies is JWST 1-14, but there are others such as Massey's Galaxy or Sears 9336 that are very old. They all have a redshift of Z at about 14, which means that they existed at a time dating back to the Dark Ages or even before. These discoveries turn our previous cosmological models upside down. According to these models, such massive and bright galaxies should not have existed at this early time in the universe. The existence of these galaxies now means two things. Either the processes of star and galaxy formation took place faster and quite differently than previously thought, or the universe is much older. At the moment, scientists have their hands full reconciling the latest discoveries with the old theories. The discovery of galaxies like JWST 14 challenges our understanding of cosmic evolution. These ancient galaxies appearing just hundreds of millions of years after the Big Bang defy conventional wisdom about how quickly structures could form in the early universe. Such findings push scientists to reconsider the timelines and mechanisms of star and galaxy formation in the universe's infancy. One of the most intriguing aspects of these discoveries is their implications for dark matter. Dark matter, although invisible and currently undetectable directly, is believed to exert gravitational influence on visible matter. Understanding its distribution in early galaxies could provide clues about its nature and role in galaxy formation. The James Webb Space Telescope, JWST, continues to be instrumental in this pursuit, leveraging its advanced instrumentation to study these distant cosmic objects with unprecedented detail. Protoglobular clusters observed within galaxies like JWST 14 offer a unique window into the early universe's star formation processes. These clusters, precursors to modern-day globular clusters, are densely packed groups of stars that formed relatively quickly from dense gas clouds. By studying their composition and dynamics, astronomers hope to unravel the conditions under which these ancient stellar nurseries emerged and evolved. Moreover, the study of early galaxies also sheds light on the epoch of reionization. This pivotal phase in cosmic history marked the transition from a neutral hydrogen-dominated universe to one where ionizing radiation from the first stars reionized the intergalactic medium. The process of reionization not only made the universe transparent but also set the stage for the formation of more complex structures like galaxies and galaxy clusters. The James Webb Telescope's ability to detect and analyze galaxies from this early era provides crucial insights into the conditions that prevailed during reionization. By pinpointing when and how these early galaxies formed, scientists can piece together a more comprehensive timeline of cosmic evolution. This includes understanding the interplay between dark matter, ordinary matter, and the energetic processes that shaped the universe's infancy. The concept of an infinite universe raises profound questions about its age and structure. If the universe is indeed infinite, it suggests that what we observe is merely a fraction of a much larger cosmos. This idea challenges our current understanding of cosmology, which is based on the observable universe's finite size and age of approximately 13.8 billion years. The implications of an infinite universe extend beyond theoretical physics into philosophical and existential realms. It forces us to reconsider our place in the cosmos and the significance of our observations within a potentially boundless expanse of space and time. It also underscores the limitations of our current observational tools in probing the true extent of cosmic reality. While the observable universe provides a vast canvas for astronomical exploration, it represents only a fraction of what may exist beyond our current detection capabilities. New generations of telescopes, such as the JWST, promise to push these boundaries further, revealing more distant and ancient objects that challenge our existing models of cosmology. The study of cosmic dawn, the period immediately following reionization, offers insights into the formation of the first galaxies and the onset of cosmic structure formation. During this epoch, the universe transitioned from a relatively uniform state to one characterized by the emergence of galaxies and clusters of galaxies. Population 3 stars, the first stars to form in the universe, played a crucial role in this transformation. These massive stars, composed primarily of hydrogen and helium, were short-lived but produced the heavy elements essential for the formation of subsequent generations of stars and planetary systems. Their formation marked a significant milestone in cosmic history, setting the stage for the diverse array of astronomical phenomena observed today. The search for population 3 stars remains a key objective of modern astronomy, as their study promises to provide critical insights into the early stages of cosmic evolution. The JWST's advanced capabilities enable astronomers to detect and characterize these ancient stellar remnants, offering clues about their formation environments and contributions to the chemical enrichment of the early universe. In addition to studying ancient galaxies and stellar populations, the JWST also contributes to our understanding of gravitational lensing. This phenomenon, predicted by Einstein's theory of general relativity, occurs when the gravitational field of a massive object, such as a galaxy cluster, bends the path of light from a more distant object. Gravitational lensing serves as a natural telescope, magnifying and distorting the light from distant galaxies and allowing astronomers to study objects that would otherwise be too faint or distant to observe directly. This technique has revolutionized our ability to explore the cosmos, revealing hidden structures and providing valuable data about the distribution of dark matter and ordinary matter in the universe. The JWST's observations of gravitational lensing events, such as those involving the cosmic GEMS arc galaxy, highlight the instrument's role in unraveling the universe's most profound mysteries. By analyzing the light deflection patterns caused by gravitational lenses, astronomers can map the distribution of mass in galaxy clusters and infer the presence of unseen dark matter. Furthermore, the JWST's infrared capabilities enable it to peer deeper into space and time than ever before. Infrared radiation, which is emitted by cooler objects and obscured by dust in the visible spectrum, reveals hidden regions of star formation and planetary systems that are inaccessible to optical telescopes. By studying infrared emissions from distant galaxies, the JWST provides insights into their chemical composition, star formation rates, and evolutionary histories. These observations contribute to our understanding of how galaxies evolve over billions of years, from their formation in the early universe to their present-day structures and interactions.